There are times when accuracy is a must, when anything less than total precision is unacceptable. Medicine, architecture, engineering, science, even sports frequently demand pinpoint accuracy.
Perhaps nowhere is precision more critical than in aviation, where lives depend on it. As aircraft maintenance personnel, your skills will provide much of that precision. This video has been created to help you identify certain precision tools and become familiar with their function, maintenance, and operation. A torque wrench, for example, is a precision tool designed to tighten fasteners to a specific value. The load or force these tools apply to the fasteners is measured in inch-pounds or foot-pounds, with the smaller torque wrenches normally scaled in inch-pounds. There are three basic types of torque wrenches: the deflecting beam, rigid frame with dial, and the audible indicating. The lever of the deflecting beam type bends or deflects when the load is applied. The torque is indicated on a scale or a dial attached to the handle. The rigid frame torque wrench has a graduated dial that indicates the applied torque. The audible indicating torque wrench has a micrometer type barrel for presetting the desired torque. When the preset torque is reached, a click is heard and an impulse can be felt in the handle. In aircraft maintenance, the torque wrenches most commonly used are the rigid frame with indicating dial and the audible indicating. When the aviation mechanic chooses the best torque wrench for the job, he considers two basic items. The range of the wrench, the amount of torque he needs to apply should fall within 30 to 80% of the wrench's range, and the calibration. The torque wrench should be calibrated in the same units as the fastener. For every fastener, there is a correct torque value. Usually, this value can be found in a standard table in the General Instructions section of the Aircraft Maintenance Manual, TM1 1500 204 23-6.
The mechanic has determined the value for the nut he must fasten. The table calls for 20 inch-pounds of torque. His wrench is a dial indicating type with a 30 inch-pound scale that can be read in inch-pounds. First, he zeroes the dial of the wrench. Then he applies even, steady downward pressure to ensure accurate torque values. Quick, jerky application of pressure will cause distortion and error. The mechanic maintains the pressure until the amount of torque required, 20 inch-pounds, is shown on the dial. Then he releases the wrench, the nut fully torqued. For working in areas where access is limited, an audible indicating torque wrench is preferred. First, preset the amount of torque called for. Do this by releasing the lock in the handle end and then rotate the grip until the correct value is reached. For this bolt, 150 inch-pounds of torque. Then apply steady, even pressure until a click is heard, indicating that the value has been reached and the torquing action is complete. When the fastener is hard to reach, the mechanic may use an attachment that extends or shortens the length of the wrench. Because these attachments alter the length of the lever, the torque value that's shown on the dial is not the actual amount that's being applied to the fastener. To determine the correct conversion, the mechanic must calculate the effect of the attachment on the torque value. He follows the formula given in the General Aircraft Maintenance Manual. The TA, or torque applied, is the value called for, and in the case of this transmission nut, the TA is 300. The TA is multiplied by L, or the length of the lever, here 10 inches. 300 times 10 is 3,000 inch-pounds. This, in turn, is divided by the lever length plus the attachment length. L, or 10, plus A, or 4, equals 14. 3,000 divided by 14 equals 214 inch-pounds. After his calculation, the mechanic knows that when his dial indicates 214 inch-pounds, the nut will have been torqued, in actual fact, to its full required value of 300. Had the mechanic been using an attachment that shortened his wrench, the formula would have been the same, except that the attachment length would have been subtracted from the lever length. Torque wrenches are precision tools and must be handled and used with care. No torque wrench should ever be loaded beyond its capacity. Audible indicating ones should be set to their minimum setting after each use. Storage should be in cool, dry places where the tool will be protected from shock and damage. If the wrench is accidentally dropped, it must be turned in to be checked for possible recalibration.
The amount of force that can be applied by a man in a wrench is limited. The man's capacity is about 100 pounds of force to a lever. If the lever is 30 inches long, the torque will be 30 times 100, or 3,000 inch-pounds, 250 foot-pounds. The size of the lever may be increased, but eventually it will be too large for the man to use. To achieve the higher torque values demanded by such fasteners as engine thrust nuts, propeller nuts, and helicopter rotor hub nuts, torque multipliers, such as this one, are used.
The aviation mechanic is preparing to torque a rotor hub retaining nut to the value specified in his manual. First, he must mount the multiplier to the hub retaining nut. To do this, he uses the torque adapter, which he fits over the nut and trunnion. He then inserts the socket and drive bar of the multiplier into the adapter. Then he positions the multiplier, secures it, and attaches the crank handle. The torque multiplier works very much like a ratchet. Turn its knob to the right, it torques or fastens. Turn the knob to the left, it loosens. The amount of torque required for the rotor hub nut is 650 foot-pounds. As he turns the handle to the right, the mechanic reads the amount of force being applied in foot-pounds on the digital indicator. When he reaches the desired value, the mechanic stops turning the handle. He watches the display for 3 minutes for torque bleed-off. If it decreases under 650, this is normal. He torques it again to the desired value and watches for bleed-off for 1 minute. He repeats the procedure one more time. 3 times, the first for 3 minutes, the second for 1 minute, and the third, if necessary, should be sufficient to achieve the required torque. To remove the holding force on the wrench, but not break the torque on the hub nut, the mechanic simply turns the crank handle to the left, counterclockwise, until the torque indicator returns to 0.
A precision tool that can play a significant role in deciding if a part is worn beyond its tolerance is this dial indicator. This tool is designed for measuring such items as bearing, radial, and axial play, propeller shaft runout, or excessive play in flight control system components. It may be used
to check wear on spline plates, drive links, out of roundness of drive shafts, and axial play of the synchronized elevator horn. Here, the aviation mechanic will use the dial indicator to check the axial play in the tail rotor pitch change link. He mounts the indicator with a special clamp and tool post holder. These are provided in the dial indicator kit and allow the tool a variety of positions. After mounting the tool, the mechanic adjusts the dial so that the reading pointer on the back of the dial makes contact with the pitch change link. He reads the dial's graduated scale, which has a measuring range from 1/1000th to 200,000ths of an inch.
when wear and damage must be assessed in a small hole, dent, or nick. Gauges that measure depth are used. The rule depth gauge is a ruler with a sliding head which can be clamped in any position. This head is ideal for bridging a hole or slot and for keeping the rule firmly perpendicular to the surface being measured. The micrometer depth gauge has a flat base which is attached to the barrel of a micrometer head. This tool can enter a 3/32 of an inch diameter hole. It can be used with a variety of extension rods which give it a range up to 9 inches. The vernier depth gauge has a sliding head and an adjustable vernier scale. This tool has the advantage of being able to enter a slot measuring 1/32 of an inch. The dial indicating depth gauge has a dial for zeroing the gauge, a lock for locking the scale reading, and a plunger which extends the measuring tool into the scratch or dent.
Here, the aviation mechanic is about to use the dial indicating depth gauge to measure a dent in a main rotor B540 metal blade. First, he slides the gauge across an area that's close to the dent. Using the dial, he zeroes the scale and then locks it into position. Then he moves the gauge over the dent and presses the plunger. He reads the scale and records the depth of the damage.
The most accurate of the adjustable measuring tools is the micrometer. There are different types of micrometers used for different jobs. An inside micrometer will measure the inside diameter of cylinders and similar hardware. An outside micrometer, such as this one, is the most often used. It measures such items as the outside diameter of shafts,
The thickness of stock, and internal oil filter elements of the engine and transmission. The micrometer most utilized is the 1-inch range. The size of the tool is given as the largest dimension it will measure. A 1-inch micrometer then measures from 0 up to 1 inch. A 5-inch micrometer measures from 4 to 5 inches. The micrometer's components include a U-shaped frame which holds the body of the tool and also supports the anvil. The ratchet top moves the steel spindle in and out of the barrel, and the lock secures the measurement on the barrel so that the reading can be taken. The barrel is calibrated in tenths of an inch. Each of the 10 spaces on the barrel equals 1/10 of an inch. The 10 spaces are then divided into 4 smaller spaces, each measuring 1/4 of 1/10 or 25 thousandths of an inch. The thimble is marked off in 25 equal spaces, each space representing 1/1000th of an inch. As the thimble turns, the spindle moves to or from the anvil. Before using the micrometer, the mechanic makes sure that there is nothing that might compromise the accuracy of the reading. He passes a clean piece of paper through the jaws of the tool to clean away any oil, fingerprints, or microscopic debris. Once this is done, he places the stock to be measured between the anvil and spindle, and turns the ratchet top until the spindle and anvil just touch the stock. He listens for the click of the ratchet, and one click only before he stops turning. Do not control the spindle by turning the barrel. This will wear out the threads. With the measurement taken, the mechanic fastens the lock which fixes the reading on the barrel. He is then able to remove the stock from the tool. To read the setting of a micrometer, the number of 1/10 inch spaces is read first. Then the 1/40th inch, then the 1/1000th inch, and if necessary for the greatest accuracy, the vernier scale or 1/10,000th inch. After each of these are read, they're added together and the measurement is determined. Here on the barrel scale, the mechanic counts the 1/10 inch lines exposed. There are 4. His first reading then is 4/10 inch or 0.4, which he records. Then he counts the number of exposed smaller spaces between that reading and the thimble. There is one exposed space, 1/40th inch or 25 thousandths of an inch. He records this number. At the 1/1000th inch scale on the thimble, he looks for the number just past the reference line. The number is 20 or 20 thousandths, which again he enters. Finally, he rotates the micrometer and reads the vernier scale to find out which lines line up exactly. The number 2 is aligned. He records 2/10,000ths of an inch or 0.0002. To obtain the micrometer reading for the stock, he adds the 4 figures together. He has determined that the stock measures 0.4452 inches. Having completed his work with the micrometer, the mechanic checks to see that the anvil and spindle are not together. Contact causes corrosion, which could damage the accuracy of this precision tool.
The propeller protractor, torque wrench and torque multiplier, depth gauge, dial indicator, and micrometer. Each of the precision tools you have seen on this program have specific applications that differ. All of these tools, however, will help you get the job done at those times when there is no substitute for accuracy.